Good evening, everyone. Today is our seventh tutorial session. Let me share my screen. Okay. Am I audible? Okay. Okay. So today is our seventh tutorial session of the course Petroleum Technology. So today we will be talking about various purification processes involved in a refinery that is associated both with the crude oil purification as well as the final product purification, the various distillate cuts that we receive from the primary processing units as well as the secondary processes. Okay. So firstly, we'll be talking about the purification processes. Then we will be talking in about bitumen and greases, their properties and their applications in different areas. And then we will be also talking about the various effluents that are given, mean the various about the effluent control or the emission control and the pollution control from the various pollutants that are released from the refinery, different refinery processes. Uh, so let us begin with the purification processes. So petroleum products are required to reach the customer in a certain degree of purity and quality. Various products, as we studied, that a crude oil consists of different cuts. It is not a like a single unit or single cut or a single product. It is a combination of different products. Crude oil consists of different cuts, different type of products, which are produced by distillation procedures, by primary processing units, and by the secondary processing units. But all of these cuts, before reaching to the market, it has to be reached to a specific degree of purity and quality. Uh, Earlier also I have mentioned that each country, each nation has some specifications. They may vary from nation to nation. These specifications of quality and purity may vary from nation to nation. For example, the octane number required for gasoline to use in motor vehicles, that can be different in India and it can be different in US. Okay, so the quality of different products, different refinery products, it varies depending on nation to nation as well. Okay. It depends on various factors like the maybe the climatic changes in different nations may also can also be the determining factor for these quality specifications, and different other factors like the quality of crude oil available in that region, or the temperature range, or the climatic conditions. All these are the like uh, 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 determining factors for deciding these quality specifications. Okay, so the impurities and undesired components may come from, as I told, that these impurities and undesired components, they may come from either from the original crude. mean either from the source or they may develop during various stages of processing, either from secondary processing or primary processing. Primary processing as they were the atmospheric distillation unit or vacuum distillation unit, and secondary processing may involve like vis breaking, coking, cracking, catalytic cracking, like thermal cracking, many reforming, many secondary processes we have studied earlier. Okay. Depending upon the nature of the crude and the ultimate use of the product, the required purification may involve a simple treatment or quite an elaborate processing. So, depending upon the quality specifications of different products, the treatment, the purification treatment, it can be a simple treatment procedure or it can be a complex treatment procedure or elaborate processing treatment. Okay. Even some feedstocks for catalytic processes require purification so that for example, uh, as I have mentioned earlier, also purification happens in different ways. Either we will do the purification of the final product, or we can also do is the most desirable and most convenient purification would be if we purify the if we remove the impurities from the source itself, like from the crude oil itself, if we make remove all the impurities, the presence of impurities in the final products will be automatically eliminated. So for that, there is an example that's feedstock in the catalytic processes like FCC. Okay, the feedstock for the catalytic processes should feedstock itself the feed that we are feeding in the FCC unit, it should be devoid from the different unwanted components or impurities, unwanted impurities. Uh, because why so? Because the catalytic process in the FCC it consists of catalytic cracking. So catalyst is involved. So if there are impurities, then this catalyst may deactivate, and it may lead to the it may degrade the efficiency of the FCC unit. Okay. Coming on to why the purification processes are very, important. Why? What is the specific aims in the purification process? So it is mainly to minimize the acidity of the products so that it may not corrode the, different reactors. Then carbon residue should be reduced. Then catalytic deactivation should be minimized so that the regeneration of the catalyst is efficient, uh, and moreover, it does not affect the efficiency of the catalytic cracking catalytic cracking unit. Okay. So mainly the main aim for purification it is to reduce the acidity of the products. Mean the feedstock as well as the products that are produced should be acidity of those products or feedstock should be less so that it may not lead to the corrosion of the reactor. Then carbon residue should be reduced so that it may not lead. If the products consist of large amount produces a very large amount of carbon residue, so what will happen? If suppose, for example, motor fuel, a fuel oil or a diesel oil is producing a large amount of carbon residue, what will happen? It will choke the engine. Okay. Then catalyst deactivation should be minimized. Impurities should be removed from the. If any procedure involves catalyst, then the feedstock itself should be devoid of all the impurities, so that it may not lead to the because these impurities will simply deactivate the catalyst and will affect the efficiency of the catalytic cracking unit or other catalytic unit. Okay. Then corrosivity should be to minimize the corrosivity. Then gum formation in gasoline, as we know, during the storage of the gasoline, gum formation takes place. So that should be reduced so that it may not lead to the choking of the engine. Then noxious combustion products, that is mainly the sulfur containing products, mainly mercaptans. They produce foul smell. Okay, so they should be removed. Okay, so the product should be devoid of the sulfur containing compounds. Then to improve burning characteristics of kerosene and diesel fuel, mean to improve its like cetane number and octane number of the kerosene and diesel fuel, so that its burning characteristics is improved and its knocking properties is enhanced. Anti-knocking properties enhanced, then gasoline properties, for example, lead susceptibility, as I told you, that the triethyl lead is used as octane enhancer in gasoline, but this lead present in this triethyl lead is very corrosive in nature. It is very toxic in nature. So if triethyl lead is used, then the engine should have good gasoline should have good lead susceptibility. Then its octane rating should be very good to improve its octane rating. Then color stability to improve the color and color stability, because each petroleum product, it has all the distillate cuts, they have some definite they should have some definite color, or mainly they are colorless or light yellowish in color. So deeper colors like brown colors or deeper colors are not advisable. Okay, so the color to improve the color and to maintain its stability, purification is required. Then odor to remove any obnoxious smell if present. Then pour point of the diesel to improve the pour point. That is basically to decrease the pour point of the diesel. All these to improve these qualities. Also, purification is required to purify the products and recover the following. And after the purification, we get various byproducts, which also from those byproducts also basically these are not byproducts. Basically, these are the unwanted, undesired materials which are present in our crude oil cuts, which are present in the distillation our various distillate cuts. So we need to remove them. But these unwanted, undesired products, after removing them, can be converted or recovered into much useful products. For example, this H2S, hydrogen disulfide, hydrogen sulfide, this gas, it is unwanted in our oil products. Okay, but this H2S can be sent to H2S recovery plant to get elemental sulfur, which is very useful. Okay, then mercaptans that can be recovered, then alkyl phenol mercaptans, which are responsible for noxious smell present in the crude oil products, or basically the LPG. Then naphthenic acids and sulfonates, all they can be removed after purifying and removing them from the crude oil products. They can be recovered to and further processed to get more useful products, to obtain more useful products. So, okay. Now coming on to H2S removal process. The removal of during the previous lectures we studied that hydrogen sulfide is the most common impurity that we get from that is mainly present in these in these crude oil distillation cuts, distillate cuts, in our lighter cuts. So as we studied that sulfur is mainly sulfur, main impurities that we talked about till now are sulfur. Components are present, nitrogen is present, oxygen is present, and some metal traces are also present. Okay. So this sulfur, it is mainly present in the form of H2S or mercaptans. Some amount of thiophene and its derivatives are also present. Okay, so these needs to be removed. Okay, if they are present in the crude oil cut, then they needs to be removed. So coming on to the H2S removal process, the removal of H2S hydrogen sulfide is done by two procedures, either by absorption or adsorption. Absorption by regenerative solvent or absorption on solid bed. So coming on to the procedure of absorption by regenerative solid, this process is based on countercurrent contact of the gas stream with the solvent. What happens is, suppose it is a tower, then solvent is given off from comes from the top, and this H2S gas is introduced from below, and counter current contact of this solvent and gas stream is uh, done. Okay, counter current contact. So this solvent will absorb the H2S present in this gas and will come down, and we will get H2S rich solvent stream. Okay. Just a second. So when H2S will this H2S will be introduced from below, and the a desirable solvent, a specific solvent will be introduced from the top that can absorb this H2S gas. And after absorbing this H2S gas from the below, we will get the H2S rich solution, or we can say H2S rich solvent. From the H2S rich solution from the absorber is then this H2S rich solvent is taken to a stripper. It is stripped of the H2S in a regenerator, usually by application of heat. So this is taken to a regenerator where it is the solution is heated. H2S and solvent solution is heated, from where we can and get the H2. We can extract the H2S gas. Okay, the regenerated lean solution is cooled, and after we separate this H2S and solvent in the regenerator, this solvent is again sent back to the is recycled back to the top of this absorber. Okay, and the H2S, the stripped acid gas rich in, and the gas and the H2S gas is usually fed to a Klaus type sulfur recovery unit where H2S is converted to elemental sulfur. Okay, so this solution, H2S rich solution, it is sent to a regenerator where H2S and this solvent is separated, and this solvent is sent back to the absorber for absorption of more H2S for the second round. And this H2S rich gas, it is sent to a sulfur recovery unit where it is converted to elemental sulfur, which can be used in various applications. Okay, and commonly used chemical solvents, as I told, that it uses a solvent. So mainly used solvents are amine and hot carbonates. In the case of hot carbonate, it is mainly potassium carbonate. Okay, potassium carbonate solution. Coming on to the second procedure, which is the adsorption procedure. Here, H2S is removal is done on the absorptive property of certain porous solid materials. Okay, and is used to selectively remove low to medium concentration of hydrogen sulfide. So mainly here porous solid materials are used. Basically, adsorbents are used. Two types of adsorbents used are non-regenerative adsorbents, where they are basically single-use adsorbents. Mainly, oxides of zinc and iron are used as porous solid materials on which H2S gets absorbed. And the regenerative type can be further regenerated for a second round, means for multiple rounds. So here mainly molecular sieves and zinc titanates are used. Okay, coming on to gasoline sweetening. So what is sweetening? As I told you earlier as well, sweetening is basically removal of, it is not basically reducing the sulfur content, but it is as the presence of sulfur impurities in a petroleum cut or the distillate cut or or here we can say gasoline. If the presence of mercaptans is there in a gasoline cut, so it gives out a foul smell. Okay, so these mercaptans provide a foul smell to the distillate cut. So we need to remove this mercaptans, or we need to either we need to remove it, or we need to convert it into some other kind of some other component. Mean basically some other chemical of sulfur containing chemical by some reaction, by some chemical reaction, so that that foul smelling mercaptan is converted into a sweet smelling compound, here basically disulfide. Okay, so basically it is simply removing the foul smell of a petroleum cut. Okay, it has been observed that straight run naphtha has low sulfur content and obtained from both sweet crude and sour crude. Sweet crude is basically which consists of mercaptans, and sour which does not consist of mercaptans. Basically, it does not have foul smell. And sour crude which has mercaptans, that is foul smelling crude. Okay, so this naphtha, as we know, it is the first liquid cut from an atmospheric distillation unit. So it is the lightest, one of the lightest cuts. So in the lightest cuts also sulfur is present, sulfur contents is present, but in a very small amount. So we can say this naphtha consists of low sulfur content. Okay, so in today's circumstances, the gasoline sulfur contents are specified at lower levels of almost at max of 10 ppm at max to mitigate the effects on catalytic converter effectiveness and to reduce exhaust emission. What is this? This is according to our country, according to Indian specifications, that is the Bharat Stage 6, which is currently followed. The specification for gasoline, the amount of sulfur which is acceptable in gasoline is 10 ppm max. Okay. Before that, it was 50 ppm, 50 ppm in Bharat Stage 5, then it was 500 ppm in Bharat Stage 4. But as the time is progressing, governments of different nations, they are becoming very much aware and concerned about the pollution and climatic issues. Therefore, this sulfur content has reduced to 10 ppm at max in Bharat Stage 6 specifications. Okay, okay. Why? So to mitigate the catalytic converter, mean to prevent the deactivation of the catalytic converter which is available in the motors in engines, so that the so that the the octane enhancers or the triethyl lead, if it is if used in the gasoline, it may not deactivate the catalytic converters present in the engines, as well as to reduce the exhaust emission. Also, if the sulfur amount is less, then the emission of sulfur dioxide will also be less. Okay, so the gasoline sweetening is used to convert mercaptans. As I told, this mercaptan, it is foul smelling, to sweet smelling disulfides. Just a second. Just give me a minute. Okay. So basically, sweetening procedure is converting of this mercaptans, which is a foul-smelling sulfur compound, to disulfide, which is sweet-smelling, with no reduction in absolute sulfur content, as it is simply conversion of mercaptans to disulfide. So the reduction of the sulfur content, there is no such reduction of the sulfur content that is going on in the this gasoline sweetening procedure. Okay. This process is only a satisfactory treating process as long as the balance of the pool that contains components with very low sulfur levels, like catalytic reformer or light straight run naphtha or alkylates or isomerates, etc., can absorb sweetened gasoline to a satisfactory sulfur level. So basically, it is telling that there is no such reduction in the sulfur content in this sweetening procedure. So it is simply a satisfactory treating process to just minimize the foul smell of the gasoline in. And if and such sweetened gasoline can be added to the gasoline pool if this small amount of sulfur levels are are acceptable, then this sweetened gasoline can be added to the gasoline pool. Okay. So what is gasoline pool? It is basically this gasoline is produced from different sections of a refinery. We get gasoline from the catalytic reformate also, then from naphtha also, then from alkylates from the alkylation unit also, then isomerate from the isomerization unit also. We get gasoline from these different units, and what happens is all these gasolines, they are blended into a a single unit, which is basically called the gasoline pool. Okay. Now coming on to another procedure, another purification procedure of this. This is also a sulfur purification procedure, which is the UOP Merox process. This Merox process controls the mercaptan sulfur. This Merox process is basically gasoline sweetening procedure only. So UOP, it is UOP Merox process. It controls the mercaptan sulfur content in a wide variety of hydrocarbon streams, from fuel gas to distillates with end point up to 345 degrees C. Okay. So this Merox process, it can convert the mercaptans present in different hydrocarbon streams, ranging from fuel gas to distillates with up to a boiling point of 345 degrees C. And the process chemistry involves, the process is based on the oxidation of mercaptans to disulfides in an alkaline environment. Okay, using oxygen supply from atmosphere in the presence of suitable organometallic catalyst. Okay, so here is the reaction. This is the mercaptan. SH is the functional unit of mercaptan. It reacts with the atmospheric oxygen in the presence of organometallic catalyst to give disulfides. Okay. So here we can see the amount of sulfur content did not reduce at all. R is a hydrocarbon chain which may be straight, branched, or cyclic, or saturated or unsaturated. Okay. So this is simply converting one type of sulfur content to another type of sulfur content without actually reducing the amount of sulfur content. Okay. Another procedure is the Merox extraction. That is the Merox process. This is Merox extraction, which is applicable to gas and straight run and thermal naphthas up to 100 degrees C. But the limitation of Merox extraction is that the cuts which has a boiling point only up to 100 degrees C, they can be processed under Merox extraction procedure. And to some extent, to FCC derived naphthas, the mercaptans are extracted with caustic soda oxidized to disulfides and removed from the system. So here, as we can see, this removed from the system, it clearly tells that the amount of sulfur content is reduced. Okay. So what happens is the mercaptans present in the distillation cuts, it is extracted using a caustic soda. caustic soda solution, and then it is oxidized to disulfide, and this disulfide is further removed from the system. Okay, there is a net reduction of the sulfur content in that product. Above this boiling point, above this 100 degrees C, the mercaptans are insufficiently soluble in caustic soda. Okay, to be for the extraction process to be practicable, and recourse is made to the sweetening process. Okay, so basically, why up to 100 degrees C? It is telling that above 100 degrees C, what will happen if the boiling point increases? Then mainly it means that the hydrocarbon length or hydrocarbon size has increased. That means that large hydrocarbons, they may be insoluble. They become insoluble in caustic soda after 100 degrees C. Okay. The sweetening process is practiced in three ways: fixed bed Maroc sweetening, minimum alkali fixed bed sweetening, and caustic free sweetening. Okay, so talking about these three different processes, that is the fixed bed Maroc sweetening. This is the flow sheet of fixed bed Maroc sweetening. This is the catalyst is supported on a bed of activated charcoal. Here the catalyst is placed, which is supported on a bed of activated charcoal and kept wet by intermittent circulation of caustic solution, and it is supported by or activated by the continuous flow of intermittent circulation of this caustic solution. Okay, okay. So this caustic solution is continuously flowing through this catalyst bed for activation. Just a second. हेलो हेलो। हाँ भेज दिया, अभी मेरी क्लास है भाई, तुम लोग इसी टाइम पे क्यों कॉल कर देते हो? ओके, okay. This is the flow sheet of fixed bed Maroc sweetening process. So here what happens is there the catalyst is it is filled with the catalyst which is supported on a bed of activated charcoal, and it is kept wet by a continuous circulation of caustic solution. Okay, the gasoline is fed and air is injected. Gasoline is fed from here. This is the gasoline feedstock, which is fed from here. Along with the air, it is fed from the top, and further the air is injected into the stream ahead of reactor, where oxidation of and when it comes in contact with this catalyst, the oxidation of mercaptans to disulfides takes place here, and after that the uh, a settler following the reaction separates the, and after the oxidation, the product is the oil is taken to this caustic settler, where the hydrocarbon and caustic solution is separated. Okay, so the caustic solution H2S is absorbed in the caustic solution, and the separation of this caustic solution and hydrocarbons takes place here, and the hydrocarbon it is sent for further filtration to the sand filter, and this caustic solution uh, it is separated from here. Okay, and then separates the settler, which is this is the settler following the reactor, separates the treated hydrocarbon and caustic. The caustic strength is typically 10 degree Bomi. This Bomi is a unit of caustic, I mean alkaline unit for measurement of the alkalinity. And this 10 degree Bomi, it is basically 6.6 weight percent of NaOH, and consumption of caustic solution is very high, which is 5 to 20 pounds of NaOH per 10,000 per 1,000 barrel of gasoline treated. Okay, so which is very high. The use of caustic is very high here, and from here after the treatment, it is after the treatment the treated hydrocarbon it is sent to the sand filter where further after filtration we get the treated product which is free from the sulfur component. Okay. Coming on to the second unit, to which is the minimal alkali fixed bed sweetening. And this minal word comes from this minimum alkali. Okay, minal. Because of the increasing difficulty and cost of spent caustic disposal. I mean, the amount of caustic solution usage is very high in this fixed bed Marox process. So, to that creates a problem of further disposal of this caustic solution. So, to because of this increasing difficulty and cost of spent caustic disposal, this Minal process is introduced, which reduces the caustic consumption down to 1 pound of NaOH per 1,000 barrels uh, of feed. Okay. The difference between this process and the standard fixed bed sweetener is the high selectivity of catalyst. Here, very high selectivity of catalyst. In catalyst of very high selectivity is used in the continuous injection and disposal of a small amount of weak caustic, which is 1.9 weight percent of NaOH is used instead of the intermittent circulation. So as we can see here, the amount of caustic is reduced a lot. Here 6.68% of NaOH was used, whereas here only 1.98% of NaOH is used. And moreover, the catalyst has better catalyst is used here. So simply, if, along with the gasoline feed itself, continuous alkalis injection of 1.9 weight percent NaOH is injected along with the feed and the air, and it goes to the reactor where here catalyst is packed, and from here we get the sweetened gasoline from below, and the caustic solution which is H2S rich caustic solution, it is circulated to a separator where the spent alkali and water is given off from the below. Some amount is recirculated, whereas the rest is given off. Okay. Coming on to the caustic free Merox. After that, also this caustic treatment, further another procedure which is the caustic free Merox. Here, complete elimination of the caustic solution was done because of the environmental pressure due to the spent caustic disposal, and a caustic free version of Merox was introduced. Here, ammonia was used to provide the alkalinity necessary for the sweetening procedure. The caustic was completely eliminated. In place of that, ammonia was used. Okay. Catalyst is more active type, and the high active state is maintained by continuous injection of a liquid activator. Okay. Here, gasoline along with air and ammonia and some amount of water is injected into the reactor from the top, and from below we get the sweetened gasoline and the uh, And the solution consisting of ammonia, water, and H2S is taken to the drain pot where it gets the waste is given off as the drain effluent and the some amount of ammonia which is given some amount it is mean some amount is drained back as liquid activator as given here. Now coming on to the hydro treatment. Another purification process, one of the most important purification process is hydro treatment. That is the so hydro treatment. It is the refinery process which involves catalytic conversion and removal of sulfur, nitrogen, oxygen, and metals from petroleum crudes and petroleum fractions at high hydrogen pressure. This hydro treatment we have studied from in all the previous lectures that the crude oil is hydro treated. So what is this hydro treatment? It is basically procedure to remove this sulfur, nitrogen, and oxygen and traces of metal from this petroleum crude by introduction by hydrogenation procedure by using high hydrogen pressure. Okay. So hydrotreatment also includes hydrogenation of unsaturates, hydrocracking of higher. It involves hydrogenation of unsaturates, that is basically making them saturated. Then hydrocracking of higher molecular weight, basically cracking of this higher molecular weight compounds of petroleum fraction to lower molecular weight compounds. Okay, that is also involved in the hydrotreatment. Basically, hydrotreatment is treatment of this petroleum crude with hydrogen, either hydrogenation or dehydrogenation that can be, takes place accordingly. The increased application of hydrotreating can be ascribed to decreasing availability of light sweet crudes. Basically, what is happening in as time is passing each day, there is this as we know there is shortage of crude that is taking place. So initially what was done that very good quality of crude was available, so everyone wanted light sweet crude which is of good quality. So mostly people mostly uh, light and sweet crude was extracted. But as the time is passing, there is this shortage of light and sweet crude. So now we have come to a fact that we need to process this heavy crude as well. Why so? Because if we do not uh, fulfill the crude need, fulfill the demand of crude, fulfill the demand of oil products in the market. These heavy crudes also needs to be processed, but we cannot use them directly. Why so? Because this light crude they are low in sulfur, nitrogen, oxygen impurities, whereas they are these four heavy crude it is very much high in sulfur, oxygen, and nitrogen impurities. So, these heavy crudes they needs to be processed in a more severe manner so that we can extract the good quality crude out of them. Okay, so this is the main one of the need of hydrotreating. Then a trend to upgrade the feedstock for catalytic reforming and catalytic cracking, because in this catalytic reforming and catalytic cracking catalyst is involved. So if we do not hydrotreat it and remove all the sulfur and nitrogen components out of it, then it may deactivate the catalyst involved in reforming and cracking procedure. So to do that we need to upgrade the feedstock of catalytic reforming and catalytic cracking procedure. Okay, and strict environmental regulations on sulfur content specifications of the fuel. Obviously, due to the environmental regulations and climatic reasons, also we need to hydrotreat our crude. This- The sulfur removal process in refinery is one of the most important units called desulfurization. Okay, this process is used to meet sulfur specifications of fuels. Okay, mean it will decrease the amount of sulfur present in the fuel to meet the sulfur specifications as according to Bharat stage 6 it is 10 ppm at max. Okay. Now the sulfides, disulfides, mercaptans, thiophenes and its higher derivatives are all objectionable sulfur compounds which are present in petroleum fractions. So these sulfides, disulfides and mercaptans, they are basically lighter sulfur compounds which are mainly present in the lighter distillate cuts of petroleum. Whereas this thiophene and its higher derivatives, they are mainly present in the heavier cuts. They may also be present in the heavier cuts, but in lesser in amount. Okay. So the sulfur reduction in petroleum fuel is gaining importance due to increasing consciousness about the serious consequences of burning sulfur bearing fuels. Okay. The Ministry of Road Transport and Highway proposed Bharat 6 emission standards equivalent to the Euro 6. Okay. Euro 6, which is used in Europe, similar to that, India has Bharat Stage 6. Okay. BS6. As per the proposed notifications, the maximum limit of gasoline diesel sulfur content should be 10 ppm for all light and heavy duty vehicles, including two or three wheelers. Now, in refinery, hydro desulfurization is done mainly to gasoline and gas oil carts to meet the sulfur specifications. The catalyst used here is the cobalt molybdenum oxide on alumina or nickel molybdenum oxide on alumina. Okay. So the hydrogen partial pressure is also an important factor. Hydrogen partial pressure is also an important factor which ranges from 20 to 40 bars depending on the type of feedstock. So these characteristics, this catalyst and this hydrogen partial pressure, they are important factors, but they may vary depending on the type of feedstock. Okay, the operating temperature may also vary between 340 at the start of the run to 370 at the end. In the addition of HDS, diesel fuel processing must also satisfy other related diesel fuel specifications such as cetane number, oxidation stability, and color throughout the HDS process. Okay. Deep HDS units are employed to saturate and open aromatic rings to improve cetane number. In case of improving cetane number, deep HDS is used, which is deep dehydrosulfurization, which is basically higher severity. Higher severity means higher partial pressure, higher hydrogen pressure, then higher temperature. All those are involved to improve the cetane number of the diesel cut. Coming on to these are some of the reactions of hydrotreatment, that is the desulfurization. Here we can see treating with the hydrogen, we get H2S and this C5H12 hydrocarbon. Here also this mercaptan, it is treated with hydrogen to give H2S and hydrocarbon. And here this disulfide is treated with H2 hydrogen to give this hydrocarbon as well and this hydrogen sulfide. And denitrification also takes place. This is here denitrification takes place and we get ammonia. And in this case also we get ammonia by treatment with hydrogen. Okay. Then hydrocarbon saturation also takes place in hydrotreatment. If we can see this here, we have an unsaturated hydrocarbon which is treated with hydrogen to give a saturated hydrocarbon. And then oxygen removal is also done by treating with hydrogen, and by removal of water vapor we get this hydrocarbon. Coming on to the types of hydrotreaters, it is quite common for a refinery to have multiple hydrotreaters. Naphtha hydrotreater hydrotreats heavy naphtha before it is fed to the reformer. This naphtha is fed to the reformer to further upgrade the naphtha. So before feeding to the reformer, where mainly catalyst is used, we need to hydrotreat it to remove the various hydrogen, various sulfur, nitrogen impurities. This heavy naphtha is hydrotreated before feeding to the reformer. Okay. Now kerosene hydrotreater hydrotreats kerosene to remove sulfur and to improve the smoke point. Mean it is kerosene is hydrotreated to remove the sulfur components as well as to improve the smoke point. How point is improved? By reducing the aromatic content. This smoke point can be improved because this aromatic content is responsible for the sooty flame. So if this by hydrotreating, what will be done, this aromatic ring will open and will be saturated. Either it will form naphthalene or it will it be converted to paraffins. Thus simply reducing this aromatics by hydrotreating will improve the smoke point of the kerosene. Okay. Distillate hydrotreater hydrotreats diesel blend stocks to remove sulfur and nitrogen and raise the cetane number. Okay. This hydrotreating will remove the sulfur and nitrogen and moreover will raise the cetane number. How so? By converting the aromatic and olefinic contents if present to saturate. As we know, good cetane number should have more saturates, basically paraffins. So by hydrotreating, this aromatics will be converted to N-paraffins and thus improve the cetane number. VGO hydrotreated hydrotreats VGO before feeding into the FCC. Why so? Because this reduces the sulfur, resulting in lower sulfur products. Mainly why? Because this FCC consists of catalytic cracking. Therefore, to eliminate the deactivation of the catalyst present in the FCC unit, we before introducing this VGO into the FCC unit, we hydrotreat the feedstock itself. Okay, FCC gasoline hydrotreater hydrotreats the FCC gasoline coming out of the FCC, which is high, also often high in sulfur. And if sometimes after the FCC also some amount of sulfur is present, then the product also we will hydrotreat to remove the sulfur content present in them. Okay. Resid hydrotreater, which is basically hydrotreats the residue, that is the atmospheric residue and vacuum residue to reduce the sulfur sometimes before sending it to the RFCC unit for upgrade. So this is the hydrotreater unit. Here it is the reactor. This is the reactor heater. Then this is the makeup compressor. Then this is the uh, makeup compressor. Then this is the recycle compressor. And then here it is the separation unit. And here separation system. Then this is the fractionator. What will happen? This fresh feed will be given from here after fresh feed along with the hydrogen from this makeup hydrogen is given of if is fed to the reactor from below, fed to the reactor from above. After exchanging heat from the final product from the reactor and this feedstock, it will exchange heat and the mixture of feedstock and hydrogen further after exchanging it, heat will be taken to the reactor heater where it will be heated to the desired temperature and further it will be introduced into the reactor from the top and where it will be treated with the hydrogen at each makeup hydrogen will be introduced at uh, each stage. And after the hydro treating, we will get the product from here, which after hydro heat exchanging from the feed will be given to the separator system, where in the separator hydrogen rich mean the source stream hydrogen rich of gases will be given off given off to here where it will be separated it into different separated mean if some amount of hydrogen is also present here it will be given off to the given off to the makeup hydrogen unit as and the makeup hydrogen unit and the liquid stream is liquid fraction from the separator system is given to the fractionator where it is separated into lighter cuts, naphtha, distillate and the hydrotreated product from below. And moreover, from the separation unit, this sour gas will be given off which consists of H2S and NH3 and different other gases. Some amount of water vapor may also be present here. Okay. Okay. Now coming on to the procedure description, hydrocarbon feedstock mixed with recycle and make up hydrogen is heated and charged to the reactor as I told, and the feedstock is desulfurized in the presence of a catalyst. The product is then stripped to remove excess hydrogen and H2S prior to fractionation. Small amount of light products than the feedstock are generally produced by cracking. Some are taken as products in the fractionation. Okay. So the importance of hydrogen. Hydrogen gas is one of the most important element present in the production of desulfurized fuels. Okay. As we have seen, hydrotreatment in the hydrotreater, mainly hydrogen gas is used at every stage. So it is a very important gas in the production of desulfurized fuel. For hydrotreating, the hydrogen stream must be extremely pure. It should be pure more than 99% and should have no humidity. The stream should have a low hydrocarbon content as well as the low mercaptan and hydrogen sulfide levels. Okay. Only about 15 to 30% of the hydrogen demand of a refinery is produced internally by processes such as catalytic reforming, and the rest is supplied by the external producers. As studied in the reforming unit, a lot of hydrogen is produced. So only 30%, up to 15 to 30% hydrogen demand of the refinery is fulfilled by the catalytic reforming or the internal units. Apart from that, 70% nitrogen is taken from the external producers. Okay, as environmental restrictions become tighter, refiner will need to explore hydrogen sources with small carbon footprint. Basically, from the reformer, then from the FCC, also sometimes some amount of hydrogen is produced. From the regenerator, we get that carbon monoxide and hydrogen, that is the synthesis gas. From there, also some amount of hydrogen is produced. But all these hydrogen produced in the refinery, it is produced with some amount of carbon with it. Therefore, which is not environmental friendly. So we need to find alternates to reduce this carbon footprint and other alternate methods to produce hydrogen, mainly, for example, like water electrolysis. Okay. Hydrotreating severity, as I told, hydrotreating severity, it is related to the more severe operations, more severe conditions. Basically, under conventional operating conditions, that is hydrogen less than 35 bar, the HDS results in a density reduction with a modest cetane number improvement. Okay, density reduction. How, as I told, sometimes in hydrotreated hydrocracking also takes place. Like more heavier hydrocarbons can crack into smaller hydrocarbons, which directly leads into a density reduction. And sometimes saturation of the aromatics also takes place, where due to which cetane number improvement takes place. During the HDS step, polycyclic aromatics are hydrogenated to mono and diaromatics, but the total aromatic concentration remains at about the same level. Okay. Consequently, the density and the ASTM D86 volume percent decreases, but the cetane gain is generally limited to around 3 points. Mean the density reduction takes place, but the cetane number improvement, it is very modest, like up to only 3 points. Okay. With regards to diesel stabilization, the typical HDS operating conditions cannot produce enough hydrodenitrification to stabilize cracked gas oil. So basically, this is for straight run naphtha. If this is for straight run products, also there is not much improvement of cetane number. And moreover, if we use cracked gas oil as the feedstock in the hydrotreater, then there will be more problems. Then the cetane number improvement and stabilization becomes a problem at less severe hydrotreating conditions. Okay, for cetane improvement and stability of diesel, the hydrogen partial pressure should increase significantly for nitrogen removal and aromatic saturation. Mean for the better cetane improvement, only sulfur removal is not enough. Nitrogen for better stability of diesel and cetane improvement, only sulfur removal is not enough. Nitrogen removal is also very important, and aromatic saturation is important. As we know that the for better cetane number, saturated the presence of N paraffins in the diesel is required. So for that purpose, only at lesser severity, lesser hydro treating severity, only sulfur removal took place, HDS took place. But for HNS to take place, like denitrification and is required and aromatic saturation is required. For that, the hydrogen partial pressure should be increased. Okay, here hydrogen partial pressure was less than 35 bar, but for more severe operation, hydrogen partial pressure should increase. So, for that purpose, deep HDS is there. The objective of deep HDS is to reach the desired sulfur specifications while improving other properties as well. That is the specific gravity, then distillation characteristics, then cetane number, the nitrogen compound contents. Okay. So hydro desulfurization light gas oil can meet all the diesel fuel specifications. As as gas oil becomes heavier, it is more difficult to meet all the specification. Mean light gas oil can be easily hydro desulfurized, whereas when the gas oil becomes heavier, then its desulfurization or hydrotreating becomes more difficult. Hydrodesulfurized heavy gas oil must be fractionated and its cetane number must be improved using a cetane booster to meet the tighter specifications. Okay, so the refiners often blend cracked gas oil with straight run naphtha followed by HDS to meet diesel demand, but the percentage of cracked gas oil is limited by the economics of the HDS process. Aromatic saturation, coming on to aromatic saturation means it is very difficult to meet the all the specifications with heavier gas oil. Okay, for that heavier gas oil, what is done, cetane boosters are added sometimes to improve the cetane number. Moreover, sometimes cracked gas oil is also blended with straight run naphtha to meet the diesel demands. Okay, so to meet the diesel demands, what is done? Cetane number should improve. Okay. For that purpose, aromatic saturation is required and cetane number improvement is there required. So the cetane number specification cannot be met by simple HDS or stability improvement. The level of severity should be increased to improve the cetane number. A nickel molybdenum type catalyst is usually employed to meet the processing objectives. The cetane number of straight run gas oil can be increased by 10 points, for example, from 53 to 63 when 65 bar hydrogen pressure is used. The severity level is important as the amount of cracked gas oil blended to straight run gas oil is increased. If this cracked gas oil is blended, then the severity level is becomes very crucial and it becomes very important, and we need to increase the severity level. If the cracked gas oil is increased and hydrotreated to meet the diesel specification for unblended cracked oil, gas oil, if we simply use the cracked gas oil only, then the cetane number is low and cannot be improved by the desired specifications with a single stage hydrotreater. When the straight run naphtha, when the light gas oil is blended with the heavy gas oil or the cracked gas oil, then severity should be made very high. It becomes very important to increase the severity because we cannot improve the cetane numbers by less severe operation, less severe hydrotreatment operation. But in case only simply cracked oil is used, then that high severity hydrotreatment also becomes ineffective. In that case, single stage hydrotreatment becomes ineffective, and we need to two stage hydrotreatment is necessary then to improve the cetane number. Okay, coming on to the another portion, that is the bitumen composition and constitution of bitumen. Okay, we have talked about bitumen in the previous classes, also in the previous lectures. Also, there we talked about the presence of bitumen in the heavier. Just a second. We have talked about the bitumen. They are the heavy, high molecular weight compounds which are present in the heavier crude oil. That is the residue part of the crude oil, mainly the atmospheric residue or the vacuum residue. Here we will be talking about the composition, constitution, and various properties of bitumen. So the properties and performance of bitumen are determined by its chemical composition, okay, and the way in which molecules interact. So where various properties and performance of bitumen in various applications depends upon its chemical composition, basically the type of crude oil it is produced and the its molecular weight, then its texture, etc. It depends. Okay, the component group of bitumens are bitumens consist of some components. The first one is asphaltenes. They are the high molecular weight complex aromatic structure with aliphatic side chains. They are basically the condensed aromatic structure which have smaller aliphatic side chains, and they can be considered as natural polymeric structures. As I told, they are the condensed aromatic polymers. Basically, mean large number of aromatic structures. They are arranged in series is with smaller aliphatic side chains. So they are basically natural polymeric structures which forms the backbone of bitumen. Higher the asphaltene content and the higher is the penetration index. This is the heaviest content and the largest amount of largest percentage of component. I mean, the asphaltene is the largest component present in the bitumen. Okay. The second component is the resin. Resins are also complex aromatic structures but with aliphatic side chains. Okay. They are also complex aromatic structures but smaller than the asphaltenes. They are soluble in N-heptanes. Mainly, they have much longer aliphatic side chains compared to the asphaltenes. They are soluble in N-heptanes and have molecular weight smaller than the asphaltenes. These asphaltenes they have a molecular weight in the range of 10 to the power 6. Okay. But here the molecular weight ranges 500 to 50,000. They form a stabilizing solvating layer around the asphaltenes. Why so solvating layer? They form a stabilizing solvating layers around the asphaltenes to stabilize their dispersion within the bitumen. To stabilize the dispersion of asphaltenes within the bitumen, basically the base oil of the bitumen. Basically, sorry, stabilize dispersion of the asphaltenes within the bitumen. And they also impart ductility to the bitumen. Okay, aromatics. When the third component is the aromatics, they are more simple aromatics, naphthenic ring structures with aliphatic side chains, and their molecular weight ranges from 300 to 2000. And fourth component is saturates. They are basically contain straight and branched aromatic hydrocarbon as well as non-aromatic ring structures or the naphthenes. The wax or paraffins are composed of the aliphatic hydrocarbons and aromatic and naphthenic structures in which the aliphatic side chains are dominant. In the case of asphaltenes and resins, aromatic rings are the dominant part. Aromatic structure are the dominant. Okay. Whereas here, aliphatic structure is dominant or aliphatic chains are dominant. Okay. A saturate fraction can be waxy or non-waxy. Coming on to the manufacture of bitumens, bitumens are manufactured from high molecular residual components that are present in petroleum crude oils. Basically, mainly they are produced from the atmospheric distillation unit and vacuum distillation. Sorry. So they are mainly produced from the atmospheric residue and vacuum residue. Okay. The residual component used for bitumen have atmospheric cut points above approximately 450 degrees C. And bitumens are divided into two broad types. This is basically atmospheric cut above 450. Why so? Because after 450 degrees C, no crude oil can sustain. They mainly decompose. Okay, so the bitumens are divided into two broad classes. They are mainly used for two broad purposes. That is the road or paving grade bitumen, and another is the industrial bitumen, mainly to make the rooftops and all for the industrial buildings, etc. And the processes that are used for bitumen production, there are three types of processes to produce bitumen. That is the vacuum distillation, oxidation, or air blowing, and another is blending. Just a second. This it is not produced bitumen mainly it is produced from the vacuum residue. Okay. So this vacuum residue It does not. This vacuum residue, it works at the vacuum. It works in the vacuum. This. Just So here this temperature is 450. It is given according to the atmosphere, whereas this in that vacuum distillation unit, it should be this vacuum distillation unit, it works in the vacuum, so their temperature is quite low compared to the atmospheric distillation unit. Whereas if we do that same procedure at the atmospheric pressure, then the temperature will be very high. Okay. Coming on to the vacuum distillation, first procedure, which is the vacuum distillation. Vacuum distillation process serves to obtain the required consistency. Consistency basically means the softness of or hardness of bitumen, and to control the volatility of the bitumen. It serves to obtain the required consistency and volatility of the bitumen. Volatile or low molecular weight materials that may be present evaporate during the bitumen application. So during the bitumen application, it is heated, and so the small lower molecular weight and volatile components it evaporate, resulting in a hardening effect and an undesirable health, safety, and environmental burden. So when this bitumen is heated for application purpose, it produces is it mean the lower molecular weight and volatile components they evaporate, leaving a very harsh smell, and hard gives a hardening effect to the bitumen. And it is very that volatiles are very that heating of the bitumen, it is very hazardous to your health, as the volatiles released out, they are very carcinogenic in nature, and such components therefore be minimized, which is so these low volatile and low molecular weight components should be very less in bitumen. Such components therefore be minimized, which is an important factor in defining minimum distillation condition for the feedstock. A typical minimum cut is 450 degrees C at 1 bar, and maximum vacuum distillation conditions are usually determined by plant design or consistency specifications of the bitumen product. And other different vacuum distillation conditions, they may vary depending on the plant design or the consistency, that is the hardness or softness of the bitumen required. Coming on to the air blowing, that is the second procedure. This is this air blowing procedure. It is the procedure which is only used here in the bitumen. It is used nowhere else in the refinery. Air blowing is an oxidation procedure that is unique to bitumen. It is applied to obtain the required viscoelastic property. This air blowing procedure is used to provide a required viscoelastic properties to the bitumen and temperature susceptibility to bitumen. Okay. Uh, Blowing is carried out at an elevated temperature between 200 to 325 degrees C. Basically, it takes place at 275 degrees C. See what happens. The oxidation is accompanied by bubbling the air throughout the bitumen via a spider fitted in the bottom of the reactor or bitumen blowing unit. Air is blown through the bitumen. With that air, oxidation of the bitumen takes place. At higher blowing temperature above 250, the oxidation reactions are predominantly dehydrogenation reactions of aromatic structure followed by polycondensation. So if this air blowing takes place at higher temperature, higher than 250, what will happen? The aromatic structures mean the dehydrogenation of the bitumen structures takes place. So as we know, bitumen consists of automatically it consists of mainly heavy hydrocarbons. Mainly aromatics are present. So these smaller hydrocarbons, okay, smaller hydrocarbons, they dehydrogenation of this aromatic structure takes place, and they form condensed aromatic structures, or maybe if there are naphthenes or paraffins are present, then dehydrogenation takes place to form condensed aromatic structures, thus increasing the quality of the bitumen more. These reactions produce and increase the molecular weight of the asphaltenes. I mean, if more condensed aromatic structures are formed, then that adds to the asphaltene content and the formation of asphaltenes from other components. This creates the viscoelasticity and temperature susceptibility properties required for bitumen. At lower blowing temperatures, the reactions are mainly direct oxidation to alcohols and oxalates. Air blowing is a key process for many industrial bitumens, which call for high degree of viscoelasticity. For paving grade bitumen, blowing is mostly applied when the bitumen obtained from vacuum distillation unit have inadequate viscoelastic properties. Okay. Bitumen blowing can be carried out in a batch mode or in continuous mode. So this is a continuous blowing mode. Here the bitumen is given from this feed is taken from here and it is introduced into the reactor blowing unit, blowing vessel from here, and compressed air is introduced from this above, which is introduced from this, which is taken to this spider fitted below, and the air is blown from below into the bitumen. Okay, and oxidation takes place here, and some steam is also introduced from the into the blowing vessel. Why? So to prevent the foaming of the bitumen in the blowing vessel, and after that the oxidized bitumen is given off from the below, which is the blown bitumen. Batch blowing. After preheating, the bitumen is fed into the blowing column. From here, the bitumen is fed into the blowing column. Air is introduced at the bottom through a spider sparger, which also serves for agitation, and the efficiency of the reaction depends on the size of the bubbles. Mean if smaller size bubbles are formed, they will give much better interaction of the bitumen with the air bubbles, and much better reaction, much better oxidation takes place. And the exothermic reaction requires for careful temperature control, and the bitumen leaves the reactor from the bottom into a surge drum. Batch blowing. Batch process is basically very simple and low in cost. A vessel is fitted with bitumen feedstock and brought to blowing temperature. Batch is simply a drum is taken and that bitumen is taken, it is heated to a desired temperature. Air is then blown through the feedstock. An exothermic reaction takes place at 200 degrees C and the heat release should be maintained. It is very crucial. The temperature of blowing must be well controlled to avoid fire or decomposition of the product. And the off gases from the product needs to be controlled with respect to the oxygen content. Batch units have a limited capacity compared to the continuous blowing units. Okay. Coming to the catalytic blowing, sometimes the blowing reaction is accelerated with the use of chemicals such as FeCl3, H3PO4, and KOH. FeCl3 acts as the oxidation promoter, then the H3PO4 forms complex molecules with resins and asphaltenes, and KOH creates association with resins and asphaltenes. A drawback of catalytic blowing is the high corrosivity of the catalyst. These catalysts may corrode the vessel in which this blowing reaction may take place, corrode the metals which is in which this blowing, may corrode the walls of the blowing vessel. Okay. And one other thing is that this we cannot exactly call it the catalytic blowing because all these are after the processing also these chemicals remain in the bitumen itself. They are not removed, so we cannot exactly call these three chemicals as catalysts. Blowing gases. In the blowing process, the gases leaving the reactor consists mainly of in blowing the gases leaving the reactor mainly consists of nitrogen, unreacted oxygen, and various other components in very small amount. The sulfur containing molecules in particular impart a obnoxious smell, and the gas need to be treated usually by burning in an incinerator. Changes in composition during oxidation. During oxidation, asphaltenes are formed from the resin fractions. As I told that the dehydrogenation takes place, so the smaller aromatic components they may break further condensed to form condensed aromatic structure. Also, higher molecular weight asphaltenes are formed from the lower molecular weight asphaltenes or from resins. Resins are formed from the aromatic fractions, and saturates they are hardly affected because they are saturated and unreactive. This explains the limit to the blowing process used for the manufacturing of certain bitumens. Increase in asphaltene content and reduction in aromatic resin fractions makes bitumen unstable. Mean if there is oxidation should also takes place into a limited manner. If excess oxidation takes place, what will happen? There will be a huge increase in the asphaltene content and reduction in the aromatic resin fraction makes bitumen unstable and asphaltene separate out from the bitumen. Okay. Bitumen application, because of its unique polymer-like properties, relative chemical inertness, and ease of application and low cost, bitumen enjoy many applications. Its function is that of a binder, adhesive, coating, sealant, and preservative. On an average, 80% of the bitumen is used in the paving application, and other 20% is used in the building and construction industry. Paving grade bitumens have a service temperature of minus 50 to 80 degrees C depending on the climate, and the industrial bitumen have a temperature range of minus 50 to 120 degrees C. Okay. Now coming on to the greases. Greases are mainly a solid to semi-solid product. Greases are mainly a solid to semi-solid product of dispersion of thickening agent in liquid lubricant. Other ingredients impart special properties may be included. Okay. Greases are lubricating oils together. Greases are mainly lubricating oils together with other components processed in a grease plant to make a gel-like material. The most important application of grease is the lubrication of rolling element bearings. Basically, where two moving parts, moving metal parts, or where two moving parts are there, moving machine parts are involved, which involves a small rolling element in between them. Their lubrication is required and grease is used. Grease has the benefit that it tends to stay where applied and can form effective seal against moisture and contaminants. It stays at where it stays to the point where it is applied, and it can also act as sealant against moisture and contaminants. Its major practical requirement is that it retains its properties under shear forces at all temperatures it experiences during use. Coming on to the grease components, it consists of mainly lubricating fuel or base oil with a thickening agent disposed in it to give a stable semi-solid product. Some additives may also be included to give grease special qualities, and typically it consists of mainly 80 to 85% of base oil, then 10 to 15% of thickener, and 5 to 10% of additives. Base oil, the selection of base oil for a particular grease has a major influence on its lubricating properties, and it is determined by the required grease characteristic. Grease made with mineral oils are suitable for the majority of applications, and due to their cost effectiveness, forms almost 95% or more of the industry use. Thickening agents, the amount and type of thickening agent used in making a grease has a significant effect on its consistency, softness, and stiffness. Principal thickeners used are the metallic soaps. Soaps are basically these are the salts made out of the by the reaction of fatty acids with the fatty acids with metal alkalis. Okay. The first greases were made with calcium and sodium soaps, and they are still used today, but lithium soaps are becoming more popular nowadays. Why? So that we will study further. Some metal soaps greases are made with a mixture of soaps. Sometimes a mixture of more than one type of soap may also be used, which is known as the mixed base greases. And other known as complex greases are also made with using a metallic soap and complexing agent using a simple organic or inorganic acid. Sometimes complex greases are also made using a metallic soap and complexing agent. Okay. A number of non-soap greases are available and are primarily used for high temperature applications. The grease used as thickeners in these, the substance used as thickeners in these greases includes bentonite, silica, powdered graphite, and other and various organic polymers. The number of non-soap greases such as the polyurea are used, and the this polyurea they consist of these thickening agents and additives. Among the additives, some important additives are detergents or dispersants to ensure the base oil and the thickeners form a stable mixture which has a uniform and consistent structure throughout. Okay. to make a stable emulsion of oil and thickener, okay, for proper dispersion of thickener in the oil. Then antioxidants to prevent oxidation of the grease. Then corrosion inhibitants to ensure the grease effectively protects the metal surface that it lubricates. Then anti-wear and EP to reduce wear and improve the load bearing capacity of the grease, because the greases they are mostly used in between the moving parts of two machines, so it should have good load bearing capacity. Then solid lubricants are also there, that is molybdenum disulfide and graphite powders are used at high temperature and heavy loads. Coming on to the properties of grease, flow properties. So when pressure is applied to grease, it does not begin to flow until a certain critical pressure is applied, that is the yield point. Until yield point is reached, you keep on applying the pressure, grease will not flow. So it is basically a non-Newtonian fluid. As further pressure is applied, the flow rate increases to a greater degree, and the viscosity of as the further pressure applies, the flow rate increases to a greater degree, and the viscosity of the grease decreases. The observed viscosity of a grease, called its apparent viscosity, varies with both temperature and flow rate. The viscosity of grease it depends both with temperature and flow rate. Okay, the apparent viscosity of grease is largely determined by the viscosity of the base oil. So mainly the viscosity of the grease it is determined mainly by the viscosity of the base oil. A knowledge of its value at a specific temperature and flow rate can help to give an idea of the handling properties of the grease. Coming on to the consistency. Consistency of a grease varies with temperature and depends principally on the amount or type of the thickener used. Consistency depends on the type and amount of the thickener used. Consistency is also influenced by the type of base oil and the conditions under which the grease is working. Grease vary from very soft, semi-solid, very soft, semi-liquid with the consistency like thick cream to hard wax like solids. Greases are commonly classified according to NLGI grading system, that is American National Lubricating Grease Institute. This system specifies 9 grades ranging from 000, that is softest, to 6, which is the stiffest. And the units are tenths of a millimeter. Coming on to the mechanical stability. Mechanical working, which usually takes place in a bearing or gearbox, can break down the structure of the grease and change its consistency. Okay. The ability of the grease to resist the changes in consistency during working is known as the mechanical stability. Unstable greases which soften excessively may leak from the bearing housing. Okay, if they are not stable, what will happen? They will during the bearing and during the bearing, it will leak out from the place it is applied. Okay, oil separation. Under certain circumstances, the base oil in a grease may separate from its thickener. Some degree of separation is essential. Sometimes some degree of separation between the thickener and base oil is necessary for providing adequate lubrication, but not complete separation. It will completely falsify the idea of lubrication. Okay. Effect of temperature. When a grease thickened with a metal soap is heated, it gradually softens until a critical temperature. Its structure breaks down and the grease liquefies. Okay. The temperature at which the liquefaction occurs, it is called the dropping point, and the maximum operating temperature of grease is considerably below the dropping point. It should be much below than the dropping point. Otherwise, what will happen? If a small amount of temperature will also increase, the grease will drop. Okay. If a grease is allowed to cool, I mean after the reaching the dropping point after being heated, if it is cooled back to its normal temperature also, then also it will not regain its original consistency. Basically, it is the plastic deformation. If a grease is cooled, it gradually hardens and eventually a point is reached at which the grease is too hard to act as a effective lubricant. Okay, so this is the cooling effect and this is the heating effect. Oxidation stability, the base oil in a grease is susceptible to oxidation in exactly the same way as the lubricating oil is. Okay, so it is susceptible to oxidation. So thickeners can also be oxidized, although they are less susceptible to oxidation than the base oil. High temperature promotes oxidation, as does active mechanical working, which increases the exposure of the grease to oxygen and generates heat. mean at high temperature grease can oxidize. Moreover, if it is subjected to very active mechanical working, then also it can oxidize during the exposure to oxygen. Okay. Water resistant greases are required for lubricating mechanism which are exposed to, if the greases are applied to machine parts which are exposed to sprays or splashes of water, then water resistant greases should be used. Corrosion protection, like other lubricants, greases are expected to provide protection against corrosion as well as to lubricate. Coming on to types of greases. Types of greases, there are mainly three types of greases. One is the lithium soap greases. They are becoming very popular nowadays. They have a characteristic smooth butter-like texture and most commonly used manufactured. They have a dropping point, very high dropping point of 170 degrees C, excellent mechanical stability and good water resistance. Okay. Whereas the calcium soap greases or lime soap greases are the oldest type of industrial greases and they have smooth texture, easy to apply, shows very good water resistance and fair mechanical stability. Okay, but they have a dropping point of around 60 degrees C, which is not good to use them at a higher temperature. Sodium soap greases or soda greases were the first high melting point greases and can be used over a wider temperature range than calcium greases, and they absorb water which gives them good rust inhibiting properties. Okay, coming on to the environmental protection. Now coming on to the environmental protection, so basically different nations have different right now different countries have become very much aware about the environmental conditions and climatic problems like pollution related issues, emission control, all that. So, for that purpose, environmental management has become a major factor for refineries, and it is important that refiners at least meet the standards set by regulatory authorities. Okay. Refineries vary enormously in the products, processes used, and types of oil process, size and throughput, location, and age. Refineries vary in what type of crude oil they are using, type of products they are producing, their size, then location, and their how much years they have set up, and the amount of, what products they are producing, amount of product they are producing. So, depending on that, different refineries have different rules and regulations that they need to meet. Okay, because of these variations, there is no such thing as the best environmental practice applicable to all refineries. There is no such general rules and regulations that everyone needs to follow, but it varies from refinery to refinery. Complete elimination of all the pollutants. It is not possible for complete elimination of the all the pollutants, but to minimize is as much as possible is required. Okay. Sometimes it is not possible to eliminate all the pollutants. Sometimes it is, suppose, for example, there are 10 pollutants that are being released in refinery, but it is not possible to eliminate all those 10. Sometimes some pollutants they become a necessity to release. So, depending on the conditions, we need to minimize the emission as much as possible. The preferred option is reduction and another thing is that the preferred option is reduction at source, which encompasses both good and operating practices and good housekeeping. It is preferred that you reduce the pollutants at the source itself, so that the processing of different crude at different stages, the secondary procedures and the primary processing, it becomes much easier. Okay. Control of atmospheric emissions. Emissions to atmosphere are the most obvious form of pollution and have been the first target for control in many countries. Okay. Consequently, there are comprehensive regulations in. Consequently, there are compress. Just a second. खुला है Consequently, there are comprehensive regulations in most part of the world to cover this topic. The quantity and the type of atmospheric emissions by refineries vary greatly depending on crude oil capacity, particular refining processes used, air pollution control measures, and the general level of maintenance and housekeeping. The principal emission sources includes combustion processes, sulfur recovery units, and catalytic cracking unit flares. I mean, the main emissions, mostly the emission comes from the combustion processes, whereas that is mainly where combustion takes place. A huge amount of flue gases are released in sulfur recovery unit. There, large amount of sulfur H2S is treated. Then catalytic cracking unit also releases large amount of flue gases and effluents. And in the flare, where huge burning of the effluent gases takes place. The main atmospheric pollutants emitted from refineries include sulfur dioxide, nitrogen dioxide, that is SOx, NOx, particulates, and volatile organic compounds, and then the CO2. Combustion related emissions. The flue gas generated from the refinery is discharged to air. Air quality regulation initially specified minimum discharge stack height to ensure good dispersion of the flue gas. So coming to combustion related emissions, the flue gas which is generated from the refinery, it is discharged into the air. So it is mainly discharged from the flare. So the length of that is the stack height where the flue gas is burnt. It should be mean quite high so that the flue gases are released very high up in the at a very considerable height for good dispersion of the flue gas into the atmosphere. In a refinery, the majority of SOx, NOx, and particulate matter emissions are directly related to the type of fuels used. Okay. Thus, the efficient use of energy is ideally a first step to control air pollution. Coming on to the SOx control, SOx emission arises from the fuels burned, catalytic cracking processes, then sulfur removal, and then recovery operations. Method of reducing these sulfur emissions are to use lower sulfur fuels and feedstock to the catalytic cracker. Alternatively, both fuel oils and feedstocks can be desulfurized by the hydrotreating as we have studied. Then H2 is formed in the processing of crude oil and other feedstock is treated in an amine treater where H2S is absorbed from refinery gases. Okay. Other sour gases containing H2S and NH3 are removed from the refinery sour water in a sour water stripper. Mean the sour water, which we get from the atmospheric distillation unit, also vacuum distillation unit, also and other various other secondary processing unit also. Oh, this sour water, it should be stripped of the H2S and NH3 before releasing it into the sending it to the ETP. These stream forms the feedstock for refinery sulfur recovery plants where elemental sulfur is, and this H2S it is further sent to the sulfur recovery unit where we can get the elemental sulfur. Okay. Coming on to the NOx control, NOx from refineries are generated mainly in the combustion processes and originate from the oxidation of both atmospheric nitrogen, that is the thermal NOx, and the indigenous nitrogen, that is the fuel NOx in the fuel. Nitrogen compounds are removed by hydrotreating prior to combustion. Okay. In addition to that, other remedial technologies such as the catalytic and non-catalytic flue gas treatments are available. A number of methods can be adopted to reduce NOx emissions, such as reducing nitrogen in feed, reducing oxygen supply so that oxygen will not come in contact with the nitrogen in the feed to form NOx, and reducing combustion temperature. The most common method is reducing residence time, which is a design feature of the burner. Coming on to the particulate control on fuel combustion, what happens if there is some ash and unburnt hydrocarbons which are present in the fuel, it will agglomerate to form particulate matters. Occasionally, flares can also be a source. Okay. It is known that with some burners, combination firing of oil and gas overall reduces. If we fire the oil and gas combined together, then it will reduce the particulate emission compared to the burning them separately. Finer atomization of fuel oil will increase the carbon burnout rate, so lower particulate emissions will occur. I mean, if the atomization of the Fuel oil is finer, that is, the smaller droplets are formed that will increase the carbon burnout rates and will lower the particulate matter. Improved air fuel mixture will improve the combustion and reduce particulates. Okay. Particulates can be a major emission from the catalytic cracking unit on cokers. The use of cyclone and electrostatic precipitators and careful catalyst selection all helps to minimize the particulate emission from these sources. Now, control of the aqueous emission, which is the potential water contaminants which are present in refinery effluents, mean there are various liquid effluents also which are present in the refinery, which includes oil and other organic materials such as acids and alkalis, sulfides, ammonia, cyanides, and heavy metals. Okay. Source control effluent treatment plant is there, which an effluent treatment plant is present in almost all refineries where liquid waste is treated there to remove all the waste elements present in the store water. So, effluent treatment plants are often classified as a treatment where all the waste water streams are collected and treated downstream of the process unit and other sources. Effluent treatment is much easier and more effective if the contaminants loading can be controlled or limited at the source. As from the starting itself, I am saying that to limit the unwanted, undesired materials at the source itself, then it becomes much easier at the product stage. Okay. In sour water stripper, H2S and NH3 are selectively stripped by the steam, which is then cooled and condensed. The off gas containing H2S and NH3 is routed to the sulfur plant. Cooling water systems, a closed cooling water network can be used where water is cooled either in a cooling tower or cooling exchangers, which is, as we know that in the refinery, heat exchanging to cool the various streams, various hot streams, cooling is required. So for that purpose, a closed cooling water network can be made to use to cool the process streams. The advantage of closed cooling water network is that is the lower water consumption rate and minimal heat pollution at final discharge. Okay. But we need to add some external chemicals in the cooling water stream because, as we know, it is a closed cooling water network. So, circulation of same water again and again. So, we need to add some external chemicals to prevent the fouling as well as the growth of bacteria and algae. We need to add some chemicals. Okay. Process operation, desalter operation provides. Desalter, you remember, as I told in the atmospheric distillation unit, before the atmospheric distillation unit, a desalter is used to remove the salts if present in the crude oil. So that desalter operation produces oily wastewater. Some amount of oil is always present. Obviously, for obvious reasons, it is very difficult to separate completely oil and water. Oily wastewater with high salt content is present, which represent a high treatment load. I mean, this high salt content will be basically a load on the ETP plant. So the load on the effluent treatment plant can be minimized if this water is first directed to a break tank where the use of demulsifiers and sufficient residence time is given so that this oil and water separates and through decantation. Okay. So after that, this oil is recovered and reprocessed because this oil is obviously very, for obvious reason, it is very, uh, expensive. So it will be recovered and reprocessed, and the water which is left after it is sent to the ETP for further treatment. Okay. Now coming on to effluent treatment, that is the solid waste which is present in every refinery. A typical refinery effluent treatment contains three main stages: primary, secondary, and tertiary treatment. Okay, primary, the first treatment in ETP is primary gross oil and solids removal. The effluent is passed through gravity separator and corrugated plates. Interceptors with the sufficient residence times to free oil. Sorry, this is for the liquid waste only. So three stages of effluent treatment are there. This is basically ETP. So then the primary stage, the removal of gross oil and solid removal is there. I mean, in the wastewater, if there is some amount of oil present, suspended oil is present, we need to remove that also. And if some solids are present, then they need to settle down. So in the gravity separator or corrugated interceptors with sufficient residence times is used so that this free oil, it will, due to the gravity, it will, density change, it will, density difference, it will come on the surface of the water and the solids will be settled down as sludge. So this pre-oil will be skimmed off and the substantial quantity of sludge can be collected in these separators. Okay. Secondary treatment as a second stage treatment, air flotation or filtration is used to remove fine oil droplets from water. If again, then also some oil droplets are left, then what will happen? Flotation unit works on the principle that oil droplets are carried to the surface by small air bubbles. Small air bubbles which attach them. Air bubbles will be introduced into the water, and these water bubbles will attach themselves to the oil droplets to form mean to coalesce the small oil droplets into bigger oil globules or suspended particles and float them to the surface from where they are removed. Okay. Chemicals such as coagulants, acids, alkalis are often added ahead of the system to promote complete removal. Mean to coagulants are added sometimes to for better collision of these oil droplets for better removal of the oil. In filtration system, the oil is filtered from the aqueous system using a filter media such as sand or anthracite. Sometimes this oil and water mixture is filtered through a sand or anthracite filter media, and after that water we get and the media is then backwashed to remove the oil that it collects. Okay. Tertiary treatment, once the majority of the free oil has been removed, biological treatments are done. So for till now, the solid and the oil waste is removed. That is physical treatment. But in the tertiary treatment, chemical treatment is done. That is the biological treatment is done to remove the water soluble constituents and water soluble impurities. Okay. So the process relies on the use of biological activity to degrade pollutants. For most wastewater, the destruction of organic materials will take place through aerobic conditions. Aerobic condition basically presence of oxygen. So most conditions we will what will takes place in aerobic condition for certain concentrated organic waste. Anaerobic condition, that is in the absence of oxygen, is done, although its applicability it is relatively very limited. The most widely used biological process for industrial wastewater is the activated sludge process. Activated sludge process, where sludge consists of a mixed blend of microorganisms, that is 95% of microorganisms are used, which are a variety of mostly aerobic species of bacteria. Okay. Bacteria which basically will digest the sludge, will digest the waste which is soluble in water. In the presence of air is used, the waste and the bacteria are held in contact long enough to stabilize the organic material and complete the desired effluent quality. Okay, so this bacteria will digest the soluble waste present in the water and will remove it. Okay. Now coming on to the solid waste, control of the solid waste, as we have studied the control of gaseous waste, then liquid waste. Now we are coming to the solid waste. Waste is defined as any solid or semi-solid material that remains as an unwanted byproduct of refining and which has to be disposed of. So first procedure is segregation of different waste, mean basically segregating different types of waste, mean separating them according to their size or like type. The most cost-effective ways to minimize waste is to control at the source. Again and again, we are repeating the same thing. That is, control the waste at the source. Since some waste generation is unavoidable, treatment of waste, particularly sludge, is required to minimize the quantity before final disposal. Some of the most common techniques used by the refiners are to dewater or de-oil sludge. Mean that sludge that we get from during the water from the ETP, we will dewater it, squeeze out the water from it, or de-oil it, squeeze it, or some amount of oil is there to decrease the quantity and recover oil from them. Sludge dewatering by gravity thickening, then the filtration, centrifugation, and by drying and heating, we will get the solid waste and we will eliminate it. The resulting waste used usually is an easily handled solid with low leachability. Mean the solid that we get out, it should have low leachability. That is, it should not leach out harmful chemicals or substances into the soil. Coming on to the assignment questions. Find out the wrong statement. The purification processes are required for petroleum products because the petroleum product should have certain degree of purity and quality. This is the correct statement. Uh, The petroleum should be transparent and devoid of any salts dissolved in them. This is kind of not correct. It is not like petroleum should be transparent. It should be devoid of colors. It should not have a foul smell. Okay. To avoid catalyst deactivation in the secondary processing unit, this is also correct, and to remove sulfur and nitrogen components from the petroleum products. So the wrong statement is this. Okay. This B is the wrong statement. Coming on to the second question, which is in the caustic free Marox process. What do we use in caustic free Marox process? In the caustic free, that is, we are not using the caustic solution. No caustic solution is used. So in that, what we use to maintain the alkalinity, we use the ammonia solution. Okay. Third question, which is the hydrogen sulfide removal process from the petroleum gas stream involves the solvent. Two types of solvents were used, that is the amine and hot carbonates were used. Okay, so amine is the correct answer. Question number four, the Bharat Stage 6 emission standards limit the maximum sulfur content in transportation fuels as I told, it is 10 mg per liter. That is 10 mg per 1000 ml. Okay, that is 10 ppm. Fifth question, find out the wrong statement. Asphaltenes are high molecular weight complex aromatic structures. This is the correct statement. Asphaltenes are mainly pure carbon particles. This is not correct. Asphaltenes have polymeric structure. Yes. Higher the asphaltene content, higher is the penetration index. This is also correct. Asphaltenes are they are not mainly just carbon particles. Okay. Sixth question, which is air blowing operation helps to improve the viscoelastic property of bitumen. As we studied, it is mainly it improves the viscoelastic property of bitumen. Okay. One of the major constituents of grease is lubricating oil, as it is almost 80 to 85% is the base oil. Okay. Consistency of a grease represents the hardness and softness of a grease, as I told you earlier. Okay. Find out the incorrect statement. Principal emission source for atmospheric pollution in the petroleum industry is. So, combustion process also produces pollution. Sulfur recovery unit also produces pollution. And catalytic cracking unit also produces pollution. Whereas this Marox process, it is basically hydrotreatment, the removal of pollutant, in fact, removal of sulfur, which is a pollutant. So, this is basically incorrect. Find out the right statement. Particulate matters are produced from ash and unburned hydrocarbon agglomeration on fuel combustion. This is correct. Particulate matter is obtained from dust particle in the air and mixture of the fuel vapor after combustion. This is not correct. When excess amount of air in the air fuel mixture increases the particulate matter. No, this is also not correct. And the formation of particulate matter can be reduced by reducing the air content in the vapor, fuel vapor. This is also not correct. So that is all for today. Thank you for your attention. Thank you.